Chapter 2, Section 3. In Chapter 2, Section 3, we have two sort of separate topics that we need to talk about. So the first one we introduce by looking at some new notation. So we know that the derivative of a function is the slope of the tangent line. Since slope is often notated change in y over change in x, we say the derivative of a function, f prime at x, is approximately the change in y over change in x. A famous mathematician, Wilhelm Leibniz, came up with an alternative notation for derivatives using this notion. If y equals f of x, then we can represent the derivative as either f prime of x, which we've been doing, or dy dx, which just means the derivative of y with respect to x. Both notations will be used to represent a derivative. So from now on, if you see dy dx, it just means take the derivative. So the first thing we want to talk about is units of a derivative. One of the reasons that our alternative notion of notation is useful is that it makes finding the units of a derivative much easier. This is generally a straightforward process, so hopefully it'll be straightforward to you as well. So, since our derivative we know is change in y over change in x, the units of the derivative will be the y units over the x units. Well, what does that mean? Let's look at a couple of examples so we can see how we set this up. Suppose that s equals f of t gives the position in miles from a point with respect to time t in hours. So here, the derivative, f prime of t, would be ds dt, derivative of the y variable position over the derivative of the t variable position. So we look at what would y represent. So here it tells us that it's s, so that would be miles, so that's what's on top. And then t is in hours, so our derivative will have the units in miles per hour. Let's look at another one. Suppose that c equals f of q gives the cost in dollars of fabric with respect to q, the number of yards. So here, in the y position, we have c, which is cost in dollars, so dollars will be our unit on top. And in the x position, we have q, which is represented by yards. So again, when we want to find the derivative, it'll be dc over dq, which is going to give us dollars per yard. So when you're given a situation, you just want to ask what the units of the y variable are and what the units of the x variable are. Obviously, it won't always be y and x, but in that general position. So in general, the units are going to be given by the units of the dependent variable, which is the one in the y position, over the units of the independent variable, which is the one in the x position. Usually it's straightforward, and hopefully it won't be too complicated for you to figure out. The other thing we have to learn about in this section is local linear approximation. This is a very useful tool to approximate things in the future. Now, this comes up quite a bit in real life, and they use this technique to do things like estimate projections for oil costs in the future or weather patterns, things like that. Anything they project in the future, they're doing some variation of local linear approximation. So suppose you own a restaurant chain. You know that when you have 5 locations open, you have 60,000 customers a year. Also, you know that for each additional restaurant you open, you'll gain 8,000 customers. Mathematically, we can write these as two statements, each as a function. Since the number of customers you have is a function of the number of locations, we can write c equals f of L, which just means customers is a function of location. Furthermore, we can take our numbers and plug them into this function to write statements. So we know that if there's 5 locations, you have 60,000 customers, so we can write f of 5 is 60,000. Now, we also know that for each additional restaurant you open, you will gain 8,000 customers. That's a rate of change. So by adding one additional unit, if you have a rate of change, that's represented by a derivative. So here, the derivative, f prime at 5, is 8,000, because you know that to go from 5 restaurants to 6, you will gain 8,000 customers. Now, if you have information about a function at a point and the derivative at a point, then we can use local linear approximation to estimate things. So let's look at how we would word the question and how we would use these in terms of the general formula for local linear approximation. The general formula looks like this. It's given as f of new equals f of old plus f prime of old times new minus old. Well, what do all these words mean and how do we plug things in? Here, new is the new number you're approximating, and old is the numbers you have. So from the example we were looking at, f of 5 would be the same thing as f of old, because that's the information you already have that you've been given, and f prime of 5 is f prime of old, because that was information given within the problem. Now we can use this to make approximations for new numbers. Let's look at a couple. So let's say we know f of 5 is 60,000 and f prime of 5 is 8,000, and then we want to use that to estimate f of 10 and f of 3. Now, let's start with f of 10. This is going to be our new number of 10 because that's the new number we want to approximate, which would represent how many customers we think we would have if we had opened 10 locations. Well, our formula says f of new equals f of old plus f prime of old times new minus old. F of new is going to be what we're looking for. So here we're looking for f of 10. Now that should equal f of old. Again, f of old is the information we were already given. So that's f of 5 plus f prime of old is f prime of 5. And then new minus old means the new number we want, which is 10, minus the old number we were using, which is 5. So then we just want to plug in numbers that we know. Well, we know that f of 5 is 60,000. That was given. Plus, we know that f prime of 5 is 8,000. And then 10 minus 5 is 5. So when we crunch all those numbers, we get 100,000. So that's our approximation for f of 10. So if we were to have 10 locations, we would approximate, by local linear approximation, that we would have 1,000 customers. Let's look at f of 3. Notice that f of 3 is a smaller number than f of 5 that we started with. So we would expect less locations than f of 5. So again, we start with the basic form of our formula. F of new equals f of old plus f prime of old times new minus old. F of new is what we want, which is f of 3. F of old is what we have, which is f of 5, plus f prime of old is f prime of 5, and then new minus old. New is 3, and the old number we're using is 5. So we plug in what we know. So we have f of 3 equals 60,000 plus 8,000 times negative 2, because new minus old gave us a negative number. That's okay. So we add those together, we get 44,000. This should make sense because the new number we want, 3, is less locations than 5, so we expect a smaller number than 60,000. So here, we'd approximate that if we only had 3 locations open, we would expect 44,000 customers. So this formula is worth writing down so that you can have it when you try to do some of these problems on homework section 3 from chapter 2.